Hello all, this is Upasana from Edureka, and in this module we are going to talk about statistics for data science. Before we begin this session, let's go through the agenda for today. So first of all, I'm going to be starting with some basic statistics, followed by some terminology related to statistics. Then we'll be talking about the categories in statistics, which is descriptive and inferential statistics. Then we'll be talking about the measures in statistics, central tendencies, and the spread. Then we'll be talking about statistics in R and why is R called the statistician's programming language. Then we'll be implementing descriptive statistics and inferential statistics in R. So without much ado, let's get straight into the module. So let's begin by defining the term statistics. So statistics is a mathematical science pertaining to the data collection, analysis, interpretation, and presentation. It is used to process complex problems in real world so that the analysts can look for meaningful trends and changes. Analysts review data so they can reach meaningful conclusions, and several statistics functions, principles, and algorithms are implemented to analyze raw data, build statistical model, and infer or predict the result. So the field of statistics has an influence over all domains of our life. The stock market, life sciences, weather, retail, insurance, and education are but to name a few. With that, let's move on to some basic terminology regarding stats. Now, there are a few statistical terms one should be aware of while dealing with data sciences. They are namely population, sample, variable, and parameter. Now, population is a set of sources which data has to be collected from. It can be a class of children, a population in a country, so on and so forth. A sample or a sample set is a subset of a wide population. You basically take a sample set, which is a chunk of the population, you apply your statistical model to them, and find out whether your conclusion holds for the entire population or no. So variable is any characteristic, number, or quantity that can be measured or counted. When it comes to your population, it can be their height, weight, income, blood group, ethnicity, language, time, so on and so forth. A variable is also called a data item. A parameter, which is also known as a statistical model, is a quantity that indexes a family of probability distributions. It can be your mean, your summation, or any element of the sample set. It basically gives you a characteristic idea about a population in general. So an analysis of any event can be done in one of two ways, quantitative and qualitative. Now, quantitative analysis or the statistical analysis is the science of collecting and interpreting data with numbers and graphs to identify patterns and trends. Qualitative or non-statistical analysis gives a generic information using text, sound, or other forms of media. So, for example, if I want a coffee from a coffee house, it is available to me in small, medium, or large. That is qualitative analysis. There is no number. But if a store sells 50 regular coffees a week, it is a quantitative analysis because we have a perfect number, we have a statistic. Although the purpose of both these analyses is to provide results, quantitative analysis provides a clearer picture, an insight if you will. It is a characteristic that makes it crucial to analytics. And that's what we are interested in. So statistical analysis has two categories. You have your descriptive and inferential statistics. Now, descriptive statistics, as you can see, uses the data to provide descriptions of population either through numerical calculations or graphs or tables. Inferential statistics, on the other hand, makes inferences or predictions about a population based on a sample of data taken from population in the same question. Now, descriptive statistics helps organize data and focuses on the characteristics of data providing parameters. Suppose you want to study the average height of students in a classroom. In descriptive statistics, you would record the heights of all the students in the class, and then you would find out the maximum, minimum, and average height of the class. Inferential statistics, on the other hand, generalizes a large data set and applies probability to arrive at a conclusion. It allows you to infer parameters of population based on simple stats and builds models on it. So, if you take the same case of finding out the height of people in a class, in inferential statistics, you will take a sample set of the class, which is basically a few people from the entire class. You already have had grouped the class into tall, average, and short, and in this method, you basically build a statistical model and expand it for the entire population in the class. Now, Let's talk a little bit about descriptive analysis. So we try to represent the data in forms of graphs and histograms and line plots, etc. But the data represented is based around some kind of central tendency, means that the particular graph represents distribution of the mean or measures of spread. Depends on what you want from your graph. So for that, we have a few measures in statistics. Let me give you an example for better understanding. So here is a sample set of cars containing variables cars, mileage per gallon, which is your MPG, cylinder type, displacement, horsepower, and real axle ratio. Using descriptive analysis, you can analyze each of the variables in the dataset for mean, standard deviation, minimum, and maximum of the range. Now, first of all, we are going to discuss a few measures of the center. These are also called measures of central tendency. Now, if we want to find out the average of horsepower of all the cars among the population of cars, we will check and calculate the average of all values. In this case, we'll take the sum of all these values and divide them by the number of cars we have. We get an answer of 103.625. So this is basically the mean of the horsepower, which is a measure of average of all values in a sample. So mean gives you an average of an entire dataset. Suppose I say the average marks in the 10th board exams of students of a certain school is 85%. Then that particular data will give us a notion that the whole school, that at an average, each student scores about 85% and the central tendency of that school is to usually perform well. Next we have median. If we want to find out the central value of MPG amongst the population of cars, we'll have to arrange all values in either ascending or descending order and choose the middle value. In this case, since we have an even number of values, which is 8 values, we take the average of the two middle values. In this case, it is 22.9. Therefore, the measure of the central value of a sample set is called a median. Next, if we want to find out our most common type of cylinder amongst the population of cars, we will check the value which is repeated most number of times. Here we can see the cylinders come in two values, one is 4 and one is 6. So the most recurring value according to the graph, as we can see, is 6. So that is our mode, which is our most recurrent value in the sample set. Now, like the measures of the center, we also have measures of the spread. This comprises of the range, interquartile range, variance, and standard deviation. So range is basically the value between the maximum and the minimum. You can see the formula is as given. Similar to the range, there's something called the interquartile range. For this, you'll have to know what is a quartile. Now, as you can see, we have a sample set from numbers 1 to 8. So basically, the purpose a quartile serves is to divide your entire data set into 4 quarters. So you have your Q1, Q2, and Q3, which are the 3 quartiles. They are your division points, and you can determine their values like so. This is your Q1, your Q2, and your Q3. As you can see, basically you take the division, the number on either side of it, and you take an average of both those numbers. And the difference between your Q1 and Q3 is basically your interquartile range. Next, we have variance. A variance basically describes how much a random variable differs from its expected value. It basically entails computing squares of deviation. I'll explain to you in just a little while. Now, there are a few crucial terms which fall under this. The first one is deviation, which is basically the difference between each element from the mean. You can see the formula is given below. Your population variance is the average of squared deviations. And you have your sample variance, which is the average of squared differences from the mean. Now, as you can see, all of these terms revolve around the mean value. This basically gives you an idea of how much an element varies or deviates from your mean value. Now we have the standard deviation, which is the final measure of spread. It is the measure of dispersion of a set of data from its mean. Since it is such an important term in statistics, we are going to find out how to take out the standard deviation. For that, we have an example. So this is basically how you should calculate a standard deviation. So let's read our problem statement. Ross has 20 dinosaur figures. They have the numbers 9, 2, 5, 4, 12, 7, 8, 11, 9, 3, 7, 4, 12, 5, 4, 10, 9, 6, 9, and 4 on them. Wow, that was a mouthful. So what we have to do is we have to work out our standard deviation. So step 1 to it is to find out the mean. The mean here is 7. As you can see, average of all the numbers divided by 20, it's 7. Next, for each number, you have to subtract the mean and square the result. Now, why are we squaring the results? Is basically to nullify any sign difference that comes in our results. As you can see in the second row, we have 2 minus 7 and the result is going to be minus 5. In such a case, if we square it, we can bring it to a positive sign. Here you can see we have 25. Same goes for the third number. Next, we work out the means of those squared differences and we get a value called sigma square. If you remember, this is also the formula for the population variance. Now, why population variance is because there's something called the degree of freedom, which is a topic for another day. But all you must know is the degree of freedom we need to subtract from the samples, and that is why we take out this value. Next, if we take a square root of sigma square, we get our sigma, which is basically our standard deviation. Our standard deviation here is 2.983. Now that we've seen the math that goes into it, let's try to work it out in R. Now, there are quite a few reasons to why the world is moving towards R. A couple of them are enlisted here. Now, R is open source and freely available. It is absolutely free and there are no hidden costs. Unlike SAS or MATLAB, you can freely install, use, update, clone, modify, redistribute, and resell R. This saves a lot of the company's money, but it also allows for easy upgrades, which is useful for statistical programming languages. Now, R is used across all platforms. So R can be run on Windows, Mac OS, and Linux. It can also import data from Microsoft Excel, Microsoft Access, MySQL, Oracle, and other programs. Next, R is a powerful scripting language. As such, R can handle large complex datasets. R is also the best language to use for heavy resource-intensive simulations, and it can be used for high-performance computer clusters. Finally, R is highly flexible and evolved. Many new developments in statistics first appeared as R packages. Now, because of these reasons, R has a huge, vibrant community and resource bank, with a global community of passionate users who regularly interact on discussion forums and attend conferences. In addition, about 2,000 free libraries are available for our unlimited use, covering statistical areas of finance, cluster analysis, high-performance computing, and much more. Now, enough chit-chat. Let's get some work done. So, RStudio. Now, R is a programming language. We use it to do statistical and quantitative analysis. So, this is RStudio. On the top left is where we write the code. Beneath it is the console. On the top right, we have our environment where we see any objects that we create. And at its bottom, we see where our plots are. Now, let's run some descriptive statistics code here. Like we saw how we take out the mean, median, and mode. I have some code here. For mean and median, we have our direct functions. Here you can see this is our data right here. We can find our median here as well. In order to get mode value, we can define our own function in R. We can just get a unique set of values and get the mode for the data set. As we can see, the mode appears right here, the function. We have printed out the mode. Now, for standard deviation, we have to take the square root of variance. As you can see, we have created an object called variance here, and the standard deviation here, we take the square root, and it appears right here with all the other objects that we've created. Now, and we can also create a histogram. All we have to do is use the function hist and pass on the parameters. Here you see we have the histogram of our data right here. Now, so far you've learnt about descriptive statistics. Let's talk a little bit about inferential statistics. So, hypothesis testing is an inferential statistical technique to determine whether there is enough evidence in a data sample to infer that a certain condition holds true for an entire population or not. To understand the characteristics of a general population, we take a random sample and analyze the properties of the sample. We test whether or not the identified conclusion represents the population accurately or not, and finally we interpret their results. Whether or not to accept the hypothesis or not depends on the percentage value that we get from the hypothesis. So let's try to understand this using a general example. Now consider 4 boys. Let's call them Nick, John, Bob, and Harry. Now all these 4 boys have to take turns in cleaning the class. Now John comes up with this genius idea of writing their names on chits and putting them in a glass bowl. Every day they would pick up a name from the bowl and that person has to clean the glass. Now it has been 3 days and everybody's name has come up except John's. Now assuming that this event is completely random and free of bias, what is the probability of John not cheating? Now if we give him the benefit of doubt, let's consider if John is not picked for a day, the probability is fairly high. We have a 3 by 4 probability, which is 75%. Now if John is not picked for 3 days in a row, the probability drops down to 0.42 approximately, which is also 42%. Now let's take a situation where John is not picked for many days in a row. Let's say 12 days in a row. The probability goes down to 0.032, which is also 3.2%. And this is what statisticians do, right? They define thresholds and say, hey, if the probability of this happening is more than 5%, then I'll consider it happening by chance. But if it is less, then given this example, John is surely cheating in some way or the other. And this number will keep dropping more and more if you increase the number of days. So this gives rise to something called null hypothesis. If your result is no different from the assumption, it is called null hypothesis. An alternate hypothesis is a result that disapproves the assumption. If a probability of an event is less than 5%, it is most probably a biased event, hence the alternate hypothesis. So I'll be using a data set and showing this to you in R. Okay, let's clear this out. Let's get our R script. Okay, so I'll be using a data set called Gapminder, so you can download it to your computers and use it simultaneously. To install the Gapminder dataset, you'll have to use install package, Gapminder, and put it in inverted commas. Now you don't have to install it every time you use it, but you've got to call it, so we use the library function. Gapminder, no inverted quotes this time. Now you can but don't have to use the data, which makes it visible on the right in your environment to view the functions. So yeah, now you can see your entire data set. So you can use the same data set to do all the descriptive statistic codes that we've run till now. But here we are going to use this for our inferential statistic codes, which is basically for hypothesis testing. You can see country, continent, year, life expectancy, population, and GDP per capita. These are the columns or variables that we have here. Okay, so we've got a data set and we might want to start by doing some manipulation. And to do that, we need to use a dplyr package. So dplyr package is one of those inbuilt packages that we need to manipulate data. Let's just install this. And again, the library function to call it. Okay, and once we've installed this, we've got access to a whole lot of sophisticated vocabulary in R. We've also got access to something called the pipe operator, which I shall explain to you about a little later in this module. So let's start by typing in Gapminder and then select the country and life expectancy. So we'll be creating a data frame, but we'll do it later. So this is what I was talking about, this percentage arrow percentage, which is also called the pipe operator because, well, it looks like a pipe. Now, pipe operator lets you pipe in your data from the left into your data in the right. So now we are going to select the country and life expectancy. And then, so this is how the pipe operator is referred to. And then we will filter. In this case, we want South Africa and Ireland. So we're just going to filter these two countries. So country, South Africa, or Ireland. We're going to run it. We're going to put this in a data frame like I had mentioned before. So we want to see how the average life expectancy differs from South Africa to Ireland. Now we want to know if this difference is statistically significant or purely by chance. Hence we do something called a t-test. So yeah, now apply the t-test to df1, which is our data frame, and compare the life expectancy. We can see our results right here. So we see the mean in the group Ireland and the mean in the group South Africa. Life expectancy differs by almost 20. 95% confidence interval lies between 15 to 22% and 23% if we take a rounded off value. So what does this tell us? If this difference between the life expectancy is in fact 0, then the probability of that happening, or P, which is the probability value, which is 4.466 into e raised to the negative of 9, which is a very, very small value. It is very, very unlikely to happen, which is almost next to impossible. Hence, it disapproves our null hypothesis. Now let's interpret this data using the ggplot2. Again, we shall install the package and tell R that we want to use it. Now we're just going to type gapminder, and then now I'm just doing this to show you how much control the pipe operator can give you. Now we want to specify the aesthetics and filter by GDP per capita. Filter by GDP, it automatically comes over. GDP per capita less than 50,000, and then we'll be specifying the aesthetics of the plot. So AS X is equal to GDP per capita, Y is equal to life expectancy. Now we want to specify the aesthetics. We want the life expectancy to map out against y-axis and the GDP per capita to map out against x-axis. So let's just run the code and see. Okay, so we use the plus sign to see what geometry needs to be used on the canvas. So I'll be using this, the geometry point. Let's run this and see. We get a basic scatter plot. To get a better graph, let's just do a log transformation of our GDP per capita and run this. Much better. Now, this looks a little bit busy, so let's just color all the dots by continent. And we can also change the size of each bubble by the population size. There you go. Looks very busy, looks very opaque. So let's just make these bubbles a little transparent. All we have to do is type alpha equals 0.6. Okay, slightly better. Let's try 0.3. By trial and error, you can basically see the kind of transparency you want. Okay, this works for me much better. Now, if we want a smooth, a linear graph, we can just add 𝐂𝐝-smooth. Let's see what that does. Yeah, it gives us lines showing a pattern or a trend in the bubbles. If you want a more linear method, all you can do is type method equals LM. We have straighter lines. Now it still looks very busy to me, so I'm just going to separate it continent-wise into different graphs. So facet, there's something called as facet wrap, and I'm going to type continent. Now that we have 5 different graphs for different continents, I think segregating them by color is not required. So let's just color this by year, shall we? Now if I zoom this, if I zoom the plot, you see that now we have one graphic which has life expectancy, GDP per capita, population size by continent and date, 5 variables in one graphic that doesn't look too busy or messy, and this is what R has to offer. Hence, it is completely a statistician's programming language. With that, I conclude my session on statistics for data science. If you have any queries, feel free to leave them in the comment section below. Thank you and have a great day ahead.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!